Tonight, we're going to confront something that should, by all rights, keep every physicist on the planet up at night. Because here's the situation. Everything you've ever seen, every star in the night sky, every galaxy our telescopes have ever photographed, every atom in your body and in the earth beneath you, all of it accounts for roughly 5% of the total mass and energy in the universe. 5%. The other 95% is something else entirely. And about 27% of that something else is a substance we call dark matter. It holds galaxies together. It shaped every large structure in the cosmos. And yet, despite decades of hunting with the most sensitive instruments humanity has ever built, no one has directly captured a single particle of it. Not because it isn't real, but because of one extraordinary property that makes it unlike anything we have ever studied. If you find this kind of deep exploration interesting, a like or subscribe would genuinely help this channel continue to exist. It's a small thing, but it makes a real difference. Now, get yourself comfortable. Let's begin. Let's start with something fundamental. What does it actually mean to detect something? To know that something is there? Think about how you experience the world every single day. You see objects because light bounces off them and enters your eyes. You feel warmth because infrared radiation reaches your skin. You hear a voice because air molecules vibrate against your eardrums. Every single sensory experience you have ever had is the result of an interaction. Something has to touch something else. Something has to push, pull, bounce, vibrate, emit, or absorb. Without interaction, there is no detection. Without detection, as far as your senses are concerned, a thing might as well not exist. Physics formalizes this in a very precise way. To detect a particle or an object, that particle or object must interact with something we can measure. It has to do something. It has to push on a detector, emit a photon, leave a track, deposit energy, trigger a chemical reaction, something. If it passes through every instrument we have without affecting anything at all, then we have no way of knowing it was ever there. Every particle that has ever been discovered in the history of physics was discovered because it interacted with something. That interaction left a trace, a signal, a footprint that we could measure and study. Throughout the history of particle physics, scientists have identified and studied the fundamental particles that make up our universe, and every single one of them interacts with the universe in ways that we can observe. The photon is the carrier of the electromagnetic force. It is light itself. Every telescope ever built, whether it detects radio waves, infrared radiation, visible light, ultraviolet, X-rays, or gamma rays, is fundamentally a device for collecting photons. The photon is how we see the universe. Without it, we will be blind to everything beyond arm's reach. The gluon carries the strong nuclear force. It binds quarks together inside protons and neutrons with a grip so powerful that no experiment has ever managed to pull a quark free. Gluons don't travel through space the way photons do. They're confined within hadrons, but their effects are measurable everywhere. The mass of a proton comes overwhelmingly from the energy of the gluon field, not from the quarks themselves. We measure the consequences of gluons every time we weigh an atom. The neutrino is the closest thing the standard model has to a ghost. It carries no electric charge. It does not interact through the strong force. The only forces it responds to are the weak nuclear force and gravity. both of which are extraordinarily feeble at the scale of individual particles. A neutrino can pass through an entire light year of solid lead without disturbing a single atom. And yet, we've detected neutrinos. We've been detecting them since 1956, when Clyde Cowan and Frederick Rains first caught them emerging from a nuclear reactor. Today, massive detectors like Super Kamiokande in Japan, filled with 50,000 tons of ultra-pure water, catch a handful of neutrino interactions every single day. The neutrino is almost impossibly elusive, but it can be caught because it does interact, however rarely, through the weak force. The electron carries electric charge and interacts electromagnetically. This is why atoms have structure. This is why chemistry exists. This is why the screen you might be looking at right now can emit light that reaches your eyes. Quarks carry both electric charge and color charge, participating in both the electromagnetic and strong forces. Protons carry positive electric charge and are held together by gluons. Neutrons, though electrically neutral overall, contain charged quarks and participate in both the strong and weak forces. A free neutron decays with a half-life of about 10 minutes and 10 seconds, revealing itself through the weak interaction by falling apart into a proton, an electron, and an antineutrino. The point is this: every known particle has at least one interaction channel that allows us to detect it. Every single one. Some interact through multiple forces, some interact through only one, but all of them interact through something. Even the neutrino, the most reluctant participant in the standard model, still shows up at the weak force party often enough that we can build detectors and catch it. Now, imagine something different. Imagine a form of matter that doesn't do any of that. Not through the electromagnetic force, not through the strong nuclear force, and if it interacts through the weak force at all, it does so at a rate so vanishingly small that decades of the most sensitive experiments ever designed have failed to catch it even once. The only force we can confirm it responds to is gravity. And gravity at the level of individual particles is almost comically weak. The gravitational attraction between two protons is roughly 10 to the 36th power weaker than the electromagnetic force between them. That's a 1 with 36 zeros. To put that number in some kind of perspective, it's roughly the ratio between the width of a single atom and the diameter of the entire observable universe. That's how much weaker gravity is than electromagnetism at the particle scale. Detecting the gravitational influence of a single particle on another single particle is so far beyond our current technology that it borders on the absurd. And yet, this is exactly the situation with dark matter. It exerts a gravitational influence. It bends the paths of stars. It warps space-time around galaxy clusters. It shaped the entire large-scale structure of the cosmos. But it does not emit light. It does not absorb light. It does not reflect light. It does not scatter light. It is completely and utterly transparent to every form of electromagnetic radiation at every wavelength. No telescope of any design, operating at any frequency from the lowest radio waves to the highest energy gamma rays, has ever detected dark matter directly. Not because those telescopes aren't sensitive enough, but because dark matter simply does not interact with the thing those telescopes are built to detect. Electromagnetic radiation passes through dark matter the way light passes through perfectly clear glass, except even more completely. because glass at least slows light down and bends it slightly. Dark matter doesn't even do that. This is the situation that has haunted physics for nearly a century. We know dark matter is there. The evidence is overwhelming, confirmed by independent observations using completely different methods. But we have never directly touched it, captured it, or measured a single particle of it in any laboratory on Earth. It is the most abundant form of matter in the universe, outweighing ordinary matter by roughly 5-1. And it is invisible to every instrument we have ever pointed at the sky. The story of how we discovered this invisible substance begins not with exotic physics or advanced mathematics, but with the simple observation that the numbers did not add up. In 1933, a Swiss-American astronomer named Fritz Zwicky was studying a massive collection of galaxies known as the Coma Cluster. The Coma Cluster is one of the richest galaxy clusters in the nearby universe, containing over 1,000 galaxies, all bound together by their mutual gravitational attraction. These galaxies orbit around the cluster's center of mass, much like planets orbit a star, except here it's entire galaxies doing the orbiting, each one containing billions of stars. Zwicky set out to do something conceptually simple. He wanted to measure the total mass of the cluster, and he had a straightforward way to do it. By measuring the speeds at which the individual galaxies were moving, within the cluster he could use Newtonian mechanics to calculate how much gravitational pull was needed to keep them in their orbits. Faster galaxies meant more gravitational pull, which meant more mass. Using the Doppler effect, the same principle that makes an ambulance siren sound higher pitched as it approaches and lower pitched as it moves away, he measured the velocities of galaxies within the Coma Cluster and calculated how much mass was required to hold the cluster together. What he found was deeply troubling. The galaxies were moving far too fast. Based on the total amount of luminous matter he could see, the stars and gas and dust visible through his telescope, there was nowhere near enough mass to account for the observed velocities. The galaxies should have been flying apart. The gravitational pull of all the visible matter combined was not even close to strong enough to keep the cluster bound. Zwicky calculated that the cluster needed roughly 400 times more mass than what was visible. 400 times. This was not a subtle discrepancy. This was not a minor calibration issue or a measurement uncertainty you could paper over with better data. Something enormous was present in that cluster that Zwicky could not see. He called this unseen component dunkle materie, dark matter. It was the first time anyone had used the term in this context, and it would eventually become one of the most important concepts in all of physics. But at the time, almost nobody paid attention. Zwicky was brilliant but abrasive. He had made enemies throughout the astronomical community. His personality was difficult, and his colleagues often dismissed his ideas simply because they didn't like him. The measurement techniques available in the 1930s were also crude by modern standards, and many astronomers assumed Zwicky's numbers were simply wrong. And perhaps most importantly, the idea itself was too strange. The claim that most of the mass in a galaxy cluster was invisible, that the universe was hiding something this fundamental from our telescopes, seemed almost absurd. The scientific community was not ready to accept it, and so Zwicky's result was largely ignored. It sat in the literature, cited occasionally but not taken seriously, for nearly 4 decades. It took until the 1970s before the evidence became impossible to dismiss, and it came from an entirely different kind of observation, one that would prove far more difficult to explain away. An American astronomer named Vera Rubin, working with instrument maker Kent Ford, began meticulously measuring the rotation speeds of spiral galaxies. A spiral galaxy rotates. Its stars and gas clouds orbit around the galactic center, pulled inward by the gravitational attraction of all the mass inside their orbit. The physics here is identical to what governs planetary orbits in our solar system. Objects closer to the central mass orbit faster. Objects farther out orbit more slowly. Mercury, the closest planet to the Sun, orbits at about 47 kilometers per second. Earth, farther out, orbits at about 30. Neptune, way out on the edge, crawls along at roughly 5. The farther you are from the central mass, the slower you orbit. This is a direct consequence of Newton's law of gravity and Kepler's laws of orbital motion. It has been confirmed by every observation of orbital mechanics ever made in the history of astronomy. Rubin and Ford expected to see exactly this pattern in galaxies. Near the center, where stars and gas are densely packed, orbital speeds should be high. As you move outward, past the bright central regions and into the sparse outer edges, where the density of visible matter drops towards zero, the orbital speeds should decline. The rotation curve, a plot of orbital speed versus distance from the center, should rise steeply near the middle and then fall off as you move outward, just like the solar system. But that is not what outward, past the bright central disk, and outward, past the bright central disk and into the dimmer outskirts. The curve did not fall. It stayed flat. Stars and gas clouds at the very edge of the galaxy, far from the bright center where most of the visible mass was concentrated, were orbiting just as fast as material much closer in. This was profoundly wrong. If the only mass present was the matter you could see through a telescope, the stars and gas and dust that emit or absorb light, the outer regions of the galaxy should have been orbiting much more slowly. The flat rotation curve meant one of two things. Either Newton's law of gravity, which had worked flawlessly for over 3 centuries, was fundamentally wrong at galactic scales, or there was enormous amounts of mass present that was not visible. Mass that extended far beyond the luminous disk of stars. Mass that did not emit, absorb, or reflect any detectable electromagnetic radiation. Rubin initially faced the same skepticism that had greeted Zwicky 40 years earlier. The idea that the majority of a galaxy's mass was invisible seemed too extraordinary. But Rubin had advantages Zwicky did not. Her measurements were precise. Her techniques were systematic. Her instruments, particularly the image tube spectrograph that Kent Ford had built, were state-of-the-art. And most importantly, her results were repeatable. She didn't measure one galaxy and make a bold claim. She measured dozens, galaxy after galaxy after galaxy, and every single one showed the same pattern. Flat rotation curves extending well beyond the visible edge of the galaxy. Not one exception. Not one galaxy that behaved the way the visible matter alone predicted. Every spiral galaxy she studied was embedded in an enormous halo of invisible mass. When other astronomers repeated her measurements using entirely different techniques, they found the same result. Radio astronomers used the 21 centimeter emission line of neutral hydrogen to trace gas clouds far beyond where optical telescopes could see stars, out into the dark, empty-looking outskirts of galaxies where no stars are visible at all. Those distant gas clouds were also orbiting far too fast. The flat rotation curves extended even farther than Rubin had measured, stretching out into regions where there was essentially no visible matter at all. Yet something was still exerting a powerful gravitational pull. By the early 1980s, the astronomical community had come to accept what Zwicky had first suggested nearly half a century earlier. Something was deeply and fundamentally wrong with our accounting of the universe's mass. Galaxies contained vastly more mass than anyone could see. Galaxy clusters contained vastly more mass than the visible galaxies within them could account for. The evidence was now arriving from multiple independent directions, each using different physics, different observations, different wavelengths of light, different assumptions, and all of them pointed to the same staggering conclusion. Something massive was out there, something invisible, something pervasive, and there was a lot of it, roughly 5 times more of it than all the ordinary matter in existence. Every proton, every neutron, every electron in every star and planet and gas cloud and dust grain in the entire observable universe was outweighed roughly 5 to 1 by this unseen substance. Everything we had ever observed directly, every galaxy we had ever photographed, every nebula we had ever studied, every atom we had ever measured, all of it was the minority component. The universe was dominated by something we could not see. This was not a small correction to our cosmic inventory. This was a fundamental upheaval. It meant that the luminous universe, the universe of stars and galaxies and glowing gas, was just the tip of an enormous iceberg. The real mass of the universe, the mass that determined its gravitational behavior and shaped its evolution, was hidden. And nobody had the faintest idea what was made of. Let me explain what the rotation curve evidence actually tells us about the structure of this invisible mass, because this is often misunderstood, and it reveals something remarkable about the consequences of dark matter's defining property. The flat rotation curves don't merely suggest that there's extra mass sprinkled around galaxies. They reveal that the distribution of this invisible mass is fundamentally different from the distribution of visible matter. In a typical spiral galaxy, the stars and gas and dust are concentrated in a flat, thin disk. The density of visible matter is highest near the center and drops off steeply as you move outward. Most of the light and most of the visible mass is contained within the central regions. This makes sense. Ordinary matter collapses into disks because it can radiate energy electromagnetically. When a cloud of gas falls inward under gravity, it heats up. That heat is radiated away as electromagnetic radiation, photons carrying energy off into space. This allows the gas to cool. Cooler gas can collapse further. Over time, this process of gravitational collapse and radiative cooling allows ordinary matter to settle into the thin, flat, rotating disks we observe as spiral galaxies. And within those disks, the densest regions collapse even further, forming the stars and planets and moons and everything else we see. Dark matter cannot do this. Because it does not interact with electromagnetic radiation, it cannot radiate away its energy. It cannot cool. When dark matter falls inward under gravity, it heats up, just as ordinary matter does. But unlike ordinary matter, it has no way to shed that heat. It cannot emit photons, It cannot glow, it cannot radiate. So the dark matter reaches a state where the random thermal motions of its particles, their kinetic energy, balances the inward pull of gravity, and it stops collapsing. It settles into a diffuse, roughly spherical halo, supported against further collapse by its own internal motions, unable to flatten into a disk because flattening requires the dissipation of energy, and energy dissipation requires electromagnetic radiation. This is why the dark matter halo of a galaxy has a completely different shape from the visible galaxy. The visible galaxy is a thin, flat disk of stars. The dark matter halo is an enormous, roughly spherical cloud of invisible mass that surrounds the entire disk and extends far beyond it in every direction. The dark matter halo of the Milky Way is estimated to extend out to roughly 300,000 light years from the galactic center, possibly even farther. The visible disk of stars spans only about 100,000 light years across. The halo is several times larger than the visible galaxy in every dimension, and it contains the majority of the galaxy's total mass. Not in stars, not in gas, not in anything we can photograph or study with any telescope. Just invisible mass, exerting its gravitational influence on everything around it while remaining perfectly transparent to every wavelength of electromagnetic radiation. This structural difference, spherical halo versus flat disk, is not incidental. It is a direct and unavoidable consequence of dark matter's defining characteristic: its inability to interact with electromagnetic radiation. That single property determines everything about how dark matter behaves on the scale of galaxies. It explains why dark matter is invisible. It explains why dark matter forms halos instead of disks. It explains why dark matter doesn't collapse into stars and planets and the complex structures that ordinary matter builds. It explains why we can detect dark matter through gravity but see nothing when we point our most powerful telescopes at the regions where we know it must be. One property, one single distinction between dark matter and everything else in our particle zoo. It does not couple to the electromagnetic force, and that distinction reshapes our entire understanding of what the universe is made of. The realization that dark matter existed didn't arrive all at once. It accumulated slowly over decades, one stubborn observation at a time, each one chipping away at the assumption that the visible universe was all there was. Zwicky noticed the first crack in 1933. Rubin and Ford turned that crack into a chasm in the 1970s. And in the decades that followed, as we will explore, the evidence continued to pile up from every direction. Gravitational lensing, the cosmic microwave background, the formation of the cosmic web, the collision of galaxy clusters. Each piece of evidence was independent of the others. Each used different physics and different observational techniques. And every single one pointed to the same extraordinary conclusion. Most of the matter in the universe is invisible. It does not emit light. It does not absorb light. It does not interact with the electromagnetic force in any measurable way. But it is there. It has mass. It pulls on things gravitationally. It bends the paths of galaxies and the fabric of space-time itself. And there is 5 times more of it than everything we have ever directly observed. The universe was hiding something enormous. And by the time the evidence became impossible to ignore, it was clear that this hidden substance wasn't just a footnote or a minor correction. It was the dominant form of matter in the cosmos, the ordinary matter we're made of, the protons and neutrons and electrons that constitute stars and planets and people, turned out to be the exception, not the rule. We are the minority. We are the 5%. And everything we see, every galaxy, every star, every world, is floating in an ocean of invisible mass that we are only now beginning to understand. Rotation curves told us something was wrong. They told us galaxies were heavier than they looked. But rotation curves alone weren't enough to settle the question. Science demands more than one line of evidence before accepting something this radical. And over the decades that followed Vera Rubin's groundbreaking measurements, astronomers found dark matter's fingerprints in places nobody expected, using methods that had nothing to do with how fast stars orbit. Each new discovery was independent of the last. Each used completely different physics. And every single one converged on the same answer. Something invisible, something massive, something that does not interact with light, permeates the universe on every scale we can measure. The next great line of evidence came from one of the most elegant predictions in all of physics. In 1915, Albert Einstein published his general theory of relativity, replacing Newton's concept of gravity as a force, acting at a distance with something far stranger and far more beautiful. Einstein showed that mass and energy don't pull on objects through some invisible tether. Instead, they warp the fabric of space-time itself. Objects move along the curved paths that this warped space-time creates, the way a marble rolls along the curved surface of a trampoline when a heavy ball sits in the middle. What we experience as gravity is not a force in the traditional sense. It's the curvature of space-time caused by the presence of mass and energy. One of the most dramatic consequences of this curvature is gravitational lensing. When light from a distant galaxy travels toward us and passes near a massive object along the way, a galaxy cluster for instance, the space-time around that cluster is curved. The light doesn't travel in a straight line. It follows the curvature, bending its path. From our vantage point on Earth, this bending acts exactly like a lens. The images of background, galaxies are distorted, stretched into arcs and rings and smeared streaks of light. Sometimes a single background galaxy appears as multiple images. Its light bent around the foreground mass along different paths, each arriving at our telescope from a slightly different direction. Einstein himself predicted this effect. It was first confirmed in 1919 during a total solar eclipse when the British astronomer Arthur Eddington measured the positions of stars that appeared near the sun's edge during the eclipse. The stars were slightly displaced from their expected positions because the sun's mass had bent their light. The displacement was tiny, only about 1.7 arc seconds, but it matched Einstein's prediction almost exactly. It was one of the most celebrated confirmations of a scientific theory in history, and it made Einstein famous overnight. But the bending caused by the sun is minuscule. The sun, massive as it is by human standards, is a single ordinary star. The truly spectacular gravitational lensing happens around much larger concentrations of mass. Galaxy clusters contain hundreds or thousands of galaxies, along with vast quantities of hot gas, all gravitationally bound together. The total mass of a galaxy cluster can be hundreds of trillions of times the mass of the sun. When light from distant galaxies passes through or near one of these massive clusters, the lensing is dramatic. Background galaxies are stretched into long, luminous arcs that curve around the cluster like fragments of a broken halo. Some are magnified enormously, allowing astronomers to see galaxies that would otherwise be too faint and too distant to detect. The cluster acts as a natural telescope, built from gravity itself. In the late 20th century, astronomers began studying these gravitational lenses with great care. And what they found was remarkable. The lensing was far too strong. The amount of bending, the degree of distortion in the background galaxy images demanded far more mass than the visible components of the clusters could provide. Astronomers could see the galaxies in the cluster. They could also see the hot intracluster gas, which glows brightly in X-rays. They could add up all the visible mass, the stars, the gas, everything that emitted or absorbed electromagnetic radiation. And it wasn't enough. Not even close. The lensing required roughly 5 to 6 times more mass than was visible. This was the same ratio Rubin had found from rotation curves. The same ratio Zwicky had estimated from galaxy velocities. But now it was being measured using an entirely different physical phenomenon. Gravitational lensing doesn't care what the mass is made of. It responds to total mass, luminous or dark, baryonic or exotic, visible or invisible. Space-time curves in response to mass and energy regardless of whether that mass emits photons. So when astronomers use lensing to map the total mass distribution of a galaxy cluster, they were seeing everything, not just the fraction that interacts with light. These lensing maps revealed that the mass in galaxy clusters extends far beyond the visible galaxies and the glowing gas. It forms enormous, roughly spherical distributions surrounding the clusters, exactly the kind of halos that dark matter was predicted to create. The visible matter, the galaxies and the X-ray emitting gas, sits in the densest central regions. But the total mass, as traced by lensing, extends much further in every direction. There's a vast envelope of invisible mass surrounding and permeating each cluster, detectable only through the way it bends the light of more distant objects. Astronomers developed increasingly sophisticated techniques to exploit this. Strong lensing, where background galaxies are dramatically distorted into arcs and multiple images, maps the mass in the densest central regions of clusters. Weak lensing, where the distortion is much more subtle, a slight statistical alignment of thousands of background galaxy shapes, maps the mass distribution over much larger areas and at greater distances from the cluster center. By combining strong and weak lensing measurements, astronomers can construct detailed two-dimensional maps of the total mass in and around galaxy clusters. These maps consistently show that most of the mass is not where the light is. The luminous matter traces out only the skeleton of a much larger mass distribution. The flesh, the bulk, the substance of these cosmic structures is invisible. Weak lensing has proven especially powerful because it could be applied not just to individual clusters, but to vast regions of the sky. Large surveys, imaging millions of background galaxies across significant fractions of the sky, have used the subtle, coherent distortions in galaxy shapes to map the distribution of total mass on enormous scales. What these surveys revealed is breathtaking. They traced out the filamentary structure of dark matter, connecting galaxy clusters across hundreds of millions of light years. The cosmic web, that vast network of filaments and voids that constitutes the largest scale structure of the universe, was laid bare not by observing the galaxies within it, but by observing how invisible mass bends the light of galaxies behind it. We can see the skeleton of the universe, and it's built from something we cannot see by any other means. But the single most dramatic piece of evidence from gravitational lensing comes from one extraordinary cosmic event. A collision between two galaxy clusters that gave us the closest thing to a direct photograph of dark matter that we have ever obtained. It's called the Bullet Cluster. Its official designation is 1E0657-56, but the name Bullet Cluster captures what happened. Two massive galaxy clusters, each containing hundreds of galaxies and enormous quantities of hot intracluster gas, collided with each other at a relative speed of roughly 4,500 kilometers per second. That's about 1.5% of the speed of light. The collision happened roughly 150 million years ago, and we observe it now in its aftermath. The two clusters having passed through each other and begun to separate on the other side. When galaxy clusters collide, three different components behave in three very different ways. First, the individual galaxies. Galaxies within each cluster are separated by enormous distances relative to their own sizes. When the two clusters pass through each other, the galaxies themselves barely interact. They're like two swarms of fireflies passing through each other in the dark. The individual fireflies are so far apart that they almost never touch. The galaxies sail through the collision largely unaffected, continuing on their original trajectories. Second, the hot intracluster gas. This gas makes up the majority of the ordinary baryonic matter in each cluster. It's a thin but incredibly hot plasma, heated to tens of millions of degrees by the gravitational energy of the cluster, glowing brightly in X-rays. Unlike the widely separated galaxies, this gas fills the space between the galaxies in a more continuous distribution. When the two gas clouds from each cluster meet, they collide. Gas interacts electromagnetically. Charged particles in the plasma interact with other charged particles. There's friction, there's pressure, there's resistance. The two gas clouds slam into each other at thousands of kilometers per second, decelerate violently, compress, heat up even further, and emit enormous quantities of X-ray radiation. The gas gets stuck. It piles up in the middle of the collision zone, slowed to a near halt by the electromagnetic interactions between its constituent particles. Third, the dark matter halos. Each cluster is surrounded by a vast halo of dark matter that contains the majority of the cluster's total mass. When the two clusters collide, these dark matter halos also pass through each other. But here's the crucial difference. Dark matter does not interact electromagnetically. It has no charge. It produces no friction. There is no pressure, no resistance, no electromagnetic coupling of any kind. The dark matter halos pass through each other as if the other weren't there, like two clouds of fog drifting through each other. Each halo continues on its original trajectory, unimpeded, carrying the majority of its cluster's mass with it. Now, astronomers observe the bullet cluster using two different methods simultaneously. They use the Chandra X-ray Observatory to image the hot gas, which glows in X-rays. And they used gravitational lensing, mapping the distortions of background galaxies to trace the distribution of total mass. The results were stunning. The X-ray images showed the hot gas concentrated in the middle of the collision, exactly between the two separating clusters. The gas from both clusters had slammed together and decelerated, pooling in the center, glowing fiercely in X-rays. This is exactly what you would expect from ordinary matter undergoing an electromagnetic collision. But the gravitational lensing maps told a completely different story. The total mass was not in the middle. It was in two distinct concentrations on either side of the gas, each roughly coinciding with the positions of the galaxies that had passed through the collision. The mass had kept going. It had sailed right through the collision without slowing down, without piling up, without interacting with the gas or with the dark matter from the other cluster. The bulk of each cluster's mass had separated from the bulk of its ordinary matter. You could see it, right there in the data. The mass was in one place. The visible matter was in another. They had physically separated during the collision because the visible matter interacts electromagnetically, and the mass, the majority of it, does not. This is extraordinarily difficult to explain without dark matter. If you believe that all mass is ordinary matter and that gravity simply works differently than Newton and Einstein predicted, then the gravitational lensing should follow the visible matter. In a modified gravity scenario, there is no invisible mass. The extra gravity comes from the matter you can see, just amplified by some modified law of physics. But in the bullet cluster, the lensing does not follow the visible matter. It follows something else. Something that separated from the gas during the collision. Something that passed right through without interacting. Something invisible. Modified gravity theories, such as modified Newtonian dynamics, were already struggling to explain certain observations by the time the bullet cluster data arrived. But the bullet cluster dealt them a particularly severe blow. It's one thing to argue that gravity might work differently in the outer regions of galaxies where accelerations are very low. It's quite another to explain why the gravitational mass of a colliding cluster is physically displaced from where the visible matter is concentrated. That displacement requires actual mass, real stuff, that has separated from the ordinary matter. And that is precisely what dark matter is. The bullet cluster is not unique. Since its discovery, astronomers have found several other galaxy cluster collisions showing similar separations between visible mass and total mass. Each one tells the same story. The gravitational mass of galaxy clusters is dominated by something that does not interact with electromagnetic radiation, something that passes through ordinary matter without friction, something that carries momentum and mass but does not emit, absorb, or scatter photons. Beyond individual clusters and their collisions, the evidence for dark matter extends all the way back to the origin of the universe. The cosmic microwave background radiation, known as the CMB, is the oldest light in existence. It was released approximately 380,000 years after the Big Bang, at a moment in cosmic history known as recombination. Before that moment, the universe was a hot, dense plasma of free protons, electrons, and photons, all mixed together. Photons couldn't travel far before scattering off a free electron. The universe was opaque, like fog. But as the universe expanded and cooled, a threshold was crossed. The temperature dropped low enough for electrons to combine with protons and form neutral hydrogen atoms. Once this happened, the photons were free. They could travel through space without constantly scattering. The fog lifted. light could finally move unimpeded across the cosmos. The photons released at that moment have been traveling ever since, stretched to longer and longer wavelengths by the expansion of space. Today, they reach us as microwave radiation with a temperature of about 2.725 Kelvin, barely above absolute zero, arriving from every direction in the sky. This radiation is not perfectly uniform. It carries tiny temperature fluctuations, variations of about 1 part in 100,000. These fluctuations are the fossilized imprint of density variations in the early universe, the seeds from which all structure would eventually grow. Regions that were slightly denser than average were slightly hotter. Regions that were slightly less dense were slightly cooler. The pattern of these fluctuations, their sizes, their amplitudes, how they relate to each other across different angular scales, encodes an extraordinary amount of information about the composition and geometry of the universe. Here is how dark matter leaves its mark on this ancient light. Before recombination, ordinary matter and photons were coupled together in the primordial plasma. They behaved as a single fluid. Gravity tried to pull ordinary matter into denser clumps, collapsing the slightly overdense regions to make them even denser. But the photons resisted. The radiation pressure of the photons pushed outward, fighting against the gravitational collapse. The result was oscillation. The coupled fluid of ordinary matter and photons oscillated, compressing and then rebounding, compressing and rebounding, like a sound wave pulsing through the plasma. These are called baryon acoustic oscillations, and they are quite literally sound waves in the early universe. Dark matter behaves completely differently. Because dark matter does not interact with photons, it does not feel radiation pressure. It is not coupled to the photon fluid. While ordinary matter is oscillating back and forth, pushed around by the photons it's locked to, dark matter simply sits in the gravitational potential wells and grows denser. Gravity pulls it inward, and nothing pushes it back out. It accumulates quietly while ordinary matter bounces around. This difference leaves a very specific and measurable signature in the CMB. The oscillations of the ordinary matter and photon fluid produce a characteristic pattern of peaks in what physicists call the CMB power spectrum, which is essentially a mathematical description of the fluctuation pattern across different angular scales. The heights and positions of these peaks depend on the relative amounts of ordinary matter, dark matter, and radiation in the early universe. More ordinary matter changes the peak heights in one way. More dark matter changes them in another. The ratio between dark matter and ordinary matter is encoded in the relative heights of the odd-numbered and even-numbered peaks. By fitting theoretical models to the observed CMB power spectrum, measured with extraordinary precision by satellites like the Cosmic Background Explorer in the early 1990s, the Wilkinson Microwave Anisotropy Probe in the 2000s, and the Planck satellite in the 2010s, cosmologists have determined the composition of the universe to remarkable accuracy. The result is consistent and unambiguous. The universe contains about 5 times more dark matter than ordinary matter. Approximately 27% of the universe's total energy content is dark matter. About 5% is ordinary baryonic matter. The remaining 68% is dark energy, which is a completely separate phenomenon from dark matter and should not be confused with it. This measurement from the CMB is completely independent of everything we've discussed so far. It has nothing to do with galaxy rotation curves, nothing to do with gravitational lensing, nothing to do with galaxy cluster dynamics or the bullet cluster. It uses entirely different physics, the behavior of sound waves in a primordial plasma, operating at an entirely different epoch in the universe's history, just 380,000 years after the Big Bang, billions of years before any galaxy or star existed. And it gives the same answer, the same ratio, roughly 5-1. Dark matter dominates the matter content of the universe. The CMB tells us something else crucial. It tells us that dark matter was essential to the formation of every structure we see in the universe today. After recombination, after the photons were released and ordinary matter decoupled from irradiation, the tiny density fluctuations imprinted in the early universe began to grow under the influence of gravity. Regions that were slightly denser than average attracted surrounding matter, becoming denser still. Over hundreds of millions of years, the densest regions collapsed to form the first gravitationally bound structures. But here is the problem. Ordinary matter alone could not have done this fast enough. Before recombination, ordinary matter was locked to the photon fluid, oscillating rather than collapsing. It could only begin to collapse freely after it decoupled from the radiation at 380,000 years. But by that point, the universe had already expanded and diluted considerably. The density fluctuations were still tiny, only about 1 part in 100,000. For these fluctuations to grow into the galaxies and galaxy clusters we observe today, they needed a head start. They needed something that had already been collapsing, something that had been building up the gravitational potential wells before ordinary matter was free to fall into them. Dark matter provided that head start. Because dark matter does not interact with electromagnetic radiation, it was never coupled to the photon fluid. It was never buffeted by radiation pressure. From the earliest moments, dark matter could respond to gravity freely. While ordinary matter was oscillating in the primordial plasma, dark matter was quietly collapsing. It was gathering in the overdense regions, deepening the gravitational potential wells, building the scaffolding into which ordinary matter would later fall. By the time recombination occurred and ordinary matter was finally free, the dark matter had already been collapsing for 380,000 years. It had already formed the dense concentrations, the dark matter halos, that would serve as the gravitational cradles for future galaxies. When ordinary matter decoupled from the photons, it didn't have to start building structure from scratch. It fell into the wells that dark matter had already prepared. The dark matter had done the heavy lifting. Ordinary matter just had to settle in. Without dark matter, the story of the universe would be completely different. The density fluctuations observed in the CMB are simply too small to have grown into the structures we see today through the gravitational collapse of ordinary matter alone, given the time available. The math doesn't work. You can run the numbers as carefully as you like, using the best models of gravitational collapse and the precise measurements of the CMB fluctuations. And the answer is always the same. Ordinary matter by itself cannot build galaxies in 13.8 billion years, starting from fluctuations of 1 part in 100,000. The growth rate is too slow. The universe expanded too fast. Without the head start provided by dark matter's early collapse, ordinary matter would still be a diffuse, structureless gas today. No galaxies, no stars, no planets, no us. This is why the large-scale structure of the universe traces the distribution of dark matter. When astronomers map the positions of galaxies across enormous volumes of space, they find that galaxies are not scattered randomly. They cluster along filaments, long thread-like structures stretching across hundreds of millions of light years. Between the filaments are vast voids, regions almost entirely devoid of galaxies. The filaments connect at nodes, dense concentrations where galaxy clusters sit. The whole structure looks like a vast cosmic web, a three-dimensional network of glowing threads separated by darkness. This web is not a coincidence. It's the direct result of dark matter's early collapse. The filaments are where dark matter collapsed first, forming elongated structures along the primordial density fluctuations. The nodes are where multiple filaments intersect, where dark matter accumulated most densely. The voids are where dark matter was slightly less dense to begin with, and from which matter was gradually pulled away toward the denser regions. Ordinary matter, freed from the photon fluid after recombination, fell into the dark matter, filaments and nodes, and formed galaxies there. The galaxies trace the dark matter. They light up the scaffolding, but the scaffolding itself is invisible. Computer simulations of cosmic structure formation confirm this picture in extraordinary detail. These simulations start with the initial conditions measured from the CMB, the density fluctuations at 380,000 years after the Big Bang. They model the gravitational evolution of both dark matter and ordinary matter over 13.8 billion years, following how matter collapses, how halos form, how filaments grow, and how galaxies assemble. The results match the observed universe remarkably well. The simulations produce cosmic webs that look strikingly similar to the real one. The distribution of galaxies, the sizes and masses of galaxy clusters, the statistical properties of the cosmic web, all are reproduced with impressive fidelity. And in every simulation, dark matter forms the scaffolding first. Ordinary matter follows. So let me bring this together. We now have 6 independent lines of gravitational evidence for dark matter. Galaxy rotation curves show that individual galaxies are embedded in massive halos of invisible matter that extend far beyond their visible disks. Galaxy cluster dynamics show that clusters contain far more mass than is visible in their galaxies and gas. Gravitational lensing maps the distribution of total mass around clusters and along the filaments of the cosmic web, consistently revealing vast quantities of invisible mass. The bullet cluster shows visible matter and total mass physically separated during a collision, providing direct visual proof that the invisible mass is real and not a modification of gravity. The cosmic microwave background encodes the ratio of dark matter to ordinary matter in its fluctuation pattern, independently confirming that dark matter outweighs ordinary matter by roughly 5-1. And the large-scale structure of the universe, the cosmic web of filaments and voids, could not have formed in the available time without dark matter collapsing first and building the gravitational scaffolding. 6 lines of evidence, different physical principles, different observational techniques, different wavelength of light, different epochs in the history of the universe, from 380,000 years after the Big Bang to the present day. Different spatial scales, from individual galaxies to the entire observable universe, and all of them point to the same conclusion. There is roughly 5 times more invisible, gravitationally active matter in the universe than the ordinary matter we can see. This invisible matter interacts through gravity. It shapes the motions of galaxies, the bending of light, the fluctuations in the oldest radiation in existence, and the architecture of the cosmos itself. But it does not interact with electromagnetic radiation in any way. It is, as we've established, completely transparent to light at every wavelength. Electromagnetically, it might as well not exist. This convergence of independent evidence is what makes the case for dark matter so compelling. It's not a single observation that could be explained away. It's not a single technique that might be flawed. It's a web of evidence, each strand independent, each pointing the same direction. If a dark matter didn't exist, you'd need a different explanation for each of these observations, and those explanations would need to be mutually consistent while also explaining why they all happen, to point to the same fictional substance. The simplest and most coherent explanation, the one that ties all the evidence together with the single hypothesis, is that dark matter is real. It exists. It has mass. It interacts gravitationally. And it does not couple to electromagnetic radiation. That last property, the inability to interact with light, is the key to everything. It explains why dark matter is invisible. It explains why it forms halos instead of disks. It explains why it could collapse before ordinary matter in the early universe. It explains why it acts as scaffolding rather than building material. It explains why galaxies trace the filaments of the cosmic web. And it raises the deepest question of all. If dark matter doesn't interact with light, if it doesn't participate in the electromagnetic force that governs everything we can see and touch and measure, then why have we never seen it? What exactly does it mean to be invisible? And is invisible the same as undetectable? Those two questions sit at the heart of everything we've been building toward. What does it mean for something to be invisible? And is invisible the same thing as undetectable? Because when most people hear that dark matter is invisible, they assume it means we can't find it. That it's some vague, hypothetical thing that might or might not exist, hiding in the shadows, evading our instruments. But that's not what's happening at all. Dark matter is not hiding. It's not evading anything. It's right here. It's everywhere. It passes through the earth, through the walls of every building, through your body, every second of every day. It's the most abundant form of matter in the universe. And we know exactly where it is, how much of it there is, and what it does to the things around it. What we cannot do is see it. And the reason we cannot see it is not a failure of our telescopes, not a limitation of our technology, not a gap in our observational capabilities. It's a fundamental property of what dark matter is. Dark matter does not couple to electromagnetic radiation. And that single fact explains everything. Let me unpack what this means. Because it is, without exaggeration, the most important sentence in this entire story. To see something, in the most general physical sense, requires electromagnetic interaction. This is true whether you're talking about your eyes, a camera, a radio telescope, an X-ray satellite, or any other instrument that has ever been used to observe the universe. Every one of these devices works by collecting electromagnetic radiation, photons, particles of light. Whether those photons have the long wavelengths of radio waves, the medium wavelengths of visible light, or the short wavelengths of X-rays and gamma rays, they are all electromagnetic radiation. They are all governed by the electromagnetic force, and they are all produced, absorbed, reflected, or scattered by particles that carry electric charge. This is a fundamental point that most people never think about. Every image of the universe you have ever seen was made of photons. Every photograph of a galaxy, every picture of a nebula, every image of a planet or a star or a cosmic event, all of them are collections of photons that traveled from the object to the detector. The Hubble Space Telescope collects photons. The James Webb Space Telescope collects photons. Radio telescopes collect photons. X-ray observatories collect photons. Gamma-ray satellites collect photons. The differences between these instruments are differences in which wavelengths of photons they collect, not in the fundamental mechanism. They are all, at their core, electromagnetic radiation detectors. For an object to be detectable by any of these instruments, it must interact with photons. It must do at least one of three things. It must emit photons, creating its own light through thermal radiation, nuclear reactions, atomic transitions, or some other process. It must absorb photons, blocking light from objects behind it and casting a shadow. Or it must scatter photons, redirecting light that passes near it and creating a detectable signal. If an object does none of these things, if photons pass through it without being emitted, absorbed, or deflected in any way, then no electromagnetic telescope can detect it. It is invisible, not faint, not dim, not hard to see, invisible, completely, fundamentally, physically invisible to the entire electromagnetic spectrum. Ordinary matter interacts with photons because it contains electrically charged particles. This is the key connection. Electromagnetic radiation is produced and absorbed by electric charges. An electron orbiting an atomic nucleus can absorb a photon and jump to a higher energy level. It can emit a photon and fall to a lower energy level. These transitions are the basis of all spectroscopy, the science that lets us determine what distant stars and galaxies are made of. A hot gas cloud emits photons because its atoms are excited. They're electrons jumping between energy levels and releasing light at specific wavelengths. A star shines because nuclear fusion in its core produces energy that works its way outward and escapes from the surface as photons. Dust absorbs photons at shorter wavelengths and re-emits them at longer infrared wavelengths. All of these processes, every single one, requires the electromagnetic force, and the electromagnetic force acts on electric charge. Every known particle participates in electromagnetic interactions, either directly through its own electric charge or indirectly through the charged quarks it contains. The electron, the quarks, the proton all carry electric charge and interact with photons. Even the neutron, which is electrically neutral overall, contains charged quarks that give it measurable electromagnetic properties. Electric charge is the universal thread connecting every known particle to the electromagnetic force. It's what allows them to emit, absorb, and scatter photons. It's what makes them visible to our instruments. The neutrino comes closest to resembling dark matter among known particles. Like dark matter, neutrinos are electrically neutral. They cannot emit, absorb, or scatter photons. You cannot photograph a neutrino at any wavelength. A neutrino is electromagnetically invisible, just like dark matter. But as we saw earlier, neutrinos have been detected because the weak force feeble as it is, gives us just enough of a handle. Out of the roughly 65 billion solar neutrinos passing through every square centimeter of a detector each second, Super Kamiokande catches about 15 per day. The rate is spectacularly low, but it is not zero, and that non-zero rate is what separates a ghost you can eventually catch from one you never will. The neutrino teaches us something vital about dark matter. The question isn't whether dark matter is elusive. It clearly is. The question is whether its non-gravitational interaction rate is merely tiny, like the neutrinos, or whether it is actually zero. Dark matter appears to be more elusive still. If dark matter interacted through the weak force at the same rate as neutrinos, we almost certainly would have detected it by now. Scientists have tried to catch it directly. For decades, experiments buried deep underground, using the most sensitive instruments ever designed, have waited for a single dark matter particle to bump into a single atomic nucleus. The result so far is silence, not one confirmed detection. This tells us that whatever dark matter is, its interaction with ordinary matter through any force beyond gravity, if such an interaction exists at all, is weaker than anything we've been able to measure. This is the fundamental challenge. The only confirmed interaction dark matter has with ordinary matter is gravitational. And gravity at the level of individual particles is almost indescribably weak. We've already seen just how feeble gravity is at the particle scale. Detecting the gravitational influence of a single dark matter particle on a single atom is so far beyond current technology that it's not even a meaningful goal to pursue. We can only detect dark matter's gravity when enormous quantities of it act collectively. When billions upon billions of dark matter particles together warp the orbits of stars, bend the paths of light, and shape the evolution of the universe. This is the distinction that matters most, and that is most often misunderstood. Dark matter is invisible, but it is not undetectable. These are not the same thing. This distinction sounds subtle, but it's everything. Let me make it concrete. Wind is invisible. You cannot see wind. You cannot photograph it. If you pointed a camera at a windy field, the wind itself would not appear in the image. But wind is absolutely not undetectable. You feel it on your skin. You see it bend the grass and shake the trees. You watch it push clouds across the sky and ripple the surface of a lake. You can measure its speed with an anemometer, its direction with a weather vane, its pressure with a barometer. Wind is invisible to your eyes, but it interacts with the world around it in ways that make its presence unmistakable. You never doubt that wind exists, even though you've never seen it, because you can feel it and observe what it does. Now, imagine something different. Imagine a substance that doesn't move the grass, doesn't shake the trees, doesn't ripple the water, doesn't push on your skin, doesn't register on any instrument that measures pressure or motion or temperature. But it does do one thing. It pulls, very gently, over enormous distances. It pulls on everything around it through gravity. You can't feel this pull directly because it's too faint at human scales. But if you watch carefully enough, over long enough distances, you notice that the stars in a galaxy are moving differently than they should. The grass isn't bending, the trees aren't shaking, but the stars are orbiting too fast. Something massive is there, pulling on them, and you cannot see what it is. That's dark matter. It's invisible like wind, in that you can't see it directly. But unlike wind, it doesn't push on anything. doesn't interact with matter through contact or pressure or electromagnetic force. It communicates only through gravity. And gravity, at the scales we experience in daily life, is far too weak to notice. You need galaxies, galaxy clusters, the bending of space-time itself, before dark matter's presence becomes apparent. But at those scales, it's unmistakable. The evidence is as clear as wind bending a tree. You just need a much bigger tree. Invisible means you cannot see it with electromagnetic radiation. No telescope can photograph it. No camera can capture it. No radio dish can pick up its signal. It produces no light. It casts no shadow. It creates no reflection. It is transparent to every photon at every wavelength in the entire electromagnetic spectrum. Undetectable means you have no way of knowing it exists. Dark matter is emphatically not undetectable. We detect it through gravity. We see its effects on the rotation of galaxies. We measure its influence on the bending of light. We observe its imprint in the cosmic microwave background. We trace its scaffolding in the cosmic web. We watch it separate from ordinary matter in cluster collisions. Gravity is a real physical interaction. It carries information. It tells us that dark matter has mass, that it occupies specific locations, that it has specific density profiles, that it forms halos of particular shapes and sizes. We know an enormous amount about dark matter from its gravitational effects alone, even though we've never captured a single particle of it. What we have not done is detect dark matter through any non-gravitational interaction. We have not caught a dark matter particle hitting an atomic nucleus. We have not observed dark matter particles annihilating each other. We have not produced dark matter in a particle accelerator. Every proposed detection method beyond gravity has so far come up empty. This is the gap. This is the open question. This is what keeps physicists searching and theorists speculating. We know dark matter exists. We can measure what it does. But we don't know what it is at the particle level, because we can't interact with it directly. Now, I want to explain why this one property, not coupling to electromagnetic radiation, has such far-reaching consequences. Because it doesn't just make dark matter invisible, it determines the entire structural role dark matter plays in the universe. It's the reason dark matter forms halos instead of stars. The reason galaxies look the way they do. The reason the cosmic web has the architecture it has. Everything flows from this one distinction. We already saw how this inability to radiate determines dark matter structure. Ordinary matter cools, collapses, and forms the thin disks and dense concentrations we observe as galaxies and stars. Dark matter cannot cool, so it remains in diffuse spherical halos, unable to compress further. But the consequences of its electromagnetic silence go far deeper than the geometry of galaxies. They cascade all the way down to the atomic scale, to the very possibility of complexity itself. Think about what this means on a cosmic scale. Dark matter cannot form atoms. Atoms exist because the electromagnetic force binds negatively charged electrons to positively charged nuclei. Without electromagnetic interaction, there is nothing to create atomic structure. No electric charge means no electromagnetic binding. No binding means no atoms. Think about what atoms actually are. An atom is not just a thing, it's a relationship. It's a negatively charged electron bound to a positively charged nucleus by the electromagnetic force. That bond is what gives atoms their size, their shape, their identity. A hydrogen atom is different from an oxygen atom not because of some label stamped on it, but because of the specific electromagnetic configuration of its electrons around its nucleus. The number of protons in the nucleus determines how many electrons the atom holds, and the arrangement of those electrons determines how the atom behaves. How it bonds with other atoms, what materials it can form, what light it absorbs and emits. Every property that makes one element different from another is electromagnetic in origin. Without the electromagnetic force, none of this exists. There are no electron orbitals, no energy levels, no spectral lines, no periodic table, no distinction between hydrogen and iron and carbon and gold. There's just mass. Featureless, structureless mass responding to gravity and nothing else. Dark matter particles, whatever they are, have mass. They move through space, they feel gravity, but they have no electromagnetic structure. They cannot bind to each other electromagnetically. They cannot form configurations with the distinct properties. Every dark matter particle is, as far as we can tell, structurally identical to every other dark matter particle of the same type. There is no dark matter equivalent of chemistry, where different arrangements of the same building blocks produce wildly different substances. There is no dark matter equivalent of water, of diamond, of air, of DNA. There is just dark matter, uniform, featureless, gravitationally active but electromagnetically silent. Without atoms, there are no molecules. Molecular bonds are electromagnetic in every form they take. A covalent bond is two atoms sharing electrons. An ionic bond is one atom stealing an electron from another, creating opposite charges that attract. Hydrogen bonds, the forces that give water its extraordinary properties and hold the two strands of DNA together, are electromagnetic. Van der Waals forces, the subtle attractions that allow geckos to walk on walls and allow proteins to fold into precise shapes, are electromagnetic. Every bond that holds any molecule together anywhere in the universe is a consequence of electromagnetic interactions between atoms. Dark matter cannot form any of these bonds. It cannot share anything, because it has no electromagnetic structure to share. It cannot attract anything electromagnetically, because it carries no charge. Two dark matter particles passing close to each other in space will feel each other's gravity, but gravity at that scale is negligible. They will drift past each other and continue on their way, unchanged, unbound, unaffected in any meaningful sense. There is no dark matter molecule, there never will be. Without molecules, there is no chemistry. And without chemistry, there is nothing that we would recognize as complexity. No liquids pooling in low places, no crystals growing from solutions, no minerals forming in cooling rock, no organic compounds assembling in warm ponds, no amino acids linking into proteins, no nucleic acids encoding information, no membranes enclosing cells, no metabolism, no reproduction, no evolution, no life, none of it. Not because dark matter is too simple or too primitive, but because all of that complexity requires the electromagnetic force, and dark matter does not have access to it. Imagine, for a moment, a universe made entirely of dark matter, no ordinary matter at all. What would it look like? It wouldn't look like anything, because looking requires light, and there would be no light. There would be no stars, because star formation requires gas cooling through electromagnetic radiation. There would be no planets, because planets are held together by electromagnetic bonds between atoms. There would be no solid surfaces, no liquids, no gases in any conventional sense. There would only be vast, smooth, diffuse halos of invisible mass drifting through an eternally dark cosmos. Gravity would pull them together into structures, filaments and halos, and a cosmic web of sorts. But those structures would have no internal detail, no complexity, no variety, just mass arranged by gravity in total silence and total darkness. Forever. That is what dark matter's universe looks like from the inside. And it is the universe we actually live in. The one that makes up 85% of all matter. We just happen to also have the 5%, the ordinary matter, the electromagnetically active fraction that brings light and complexity and life into the picture. Without atoms, there are no molecules. Molecular bonds are electromagnetic. Covalent bonds, ionic bonds, hydrogen bonds, van der Waals forces. Every type of chemical bond depends on the electromagnetic interactions between atoms. No atoms, no molecules. Without molecules, there is no chemistry. Chemistry is the science of how molecules interact, break apart and recombine. It is driven entirely by electromagnetic forces. No molecules means no chemical reactions. No chemical reactions of any kind. Without chemistry, there are no complex structures, no crystals, no minerals, no liquids in any conventional sense, no proteins, no nucleic acids, no cells, no life. At least no life as we understand it. Everything that makes ordinary matter interesting. Everything that allows it to form the extraordinary diversity of structures we see around us, from snowflakes to stars to living organisms, all of it depends on the electromagnetic force. Dark matter is excluded from all of it. It cannot participate. It exists in a parallel structural universe, governed by gravity alone, unable to access the rich complexity that electromagnetism provides. This might sound like a limitation, and in one sense it is. Dark matter will never form a planet. It will never form a star. It will never assemble into anything remotely resembling life. But in another sense, this limitation is precisely what makes dark matter so important to the universe as we know it. Because dark matter cannot cool, it collapses first and then stops. It forms the gravitational wells, the potential energy valleys into which ordinary matter later falls. It creates the scaffolding. And because dark matter is about 5 times more abundant than ordinary matter, that scaffolding is the dominant structure. The architecture of the universe, the cosmic web of filaments and voids and nodes, is primarily a dark matter architecture. Ordinary matter is the secondary component that follows dark matter's lead, falling into the structures dark matter built, and then doing something dark matter cannot, cooling, collapsing further, and forming the dazzling complexity of stars and galaxies and worlds. If a dark matter could interact electromagnetically, if it could cool and collapse the way ordinary matter does, the universe would be unrecognizable. Dark matter would have formed its own stars, its own planets, perhaps its own chemistry and its own biology. It would compete with ordinary matter for gravitational dominance within galaxies. The neat separation between dark scaffolding and luminous building would not exist. The cosmic web might look completely different. Galaxy formation might proceed in entirely different ways. The universe we know, with its specific arrangement of visible galaxies tracing invisible filaments, depends critically on dark matter being electromagnetically inert. There is an analogy that might help here. Think of dark matter as the foundation and framing of a building, the steel beams and concrete footings that determine the building's shape, its height, where the walls go, where the flaws are. Now think of ordinary matter as the interior, the drywall, the plumbing, the wiring, the furniture, the people inside. The foundation determines the structure. Without it, nothing else could exist in that configuration. But the foundation itself is hidden. You don't see the steel beams when you walk through a finished building. You see the walls, the floors, the fixtures. The visible parts are the minority of the total structure. But they're the parts you interact with. They're the parts that matter to your daily experience. Dark matter is the hidden frame of the universe. Ordinary matter is the visible interior. The frame came first. The interior was built within it. The frame is larger and more massive. The interior is smaller, but infinitely more complex. And you can only see the interior, never the frame, because the frame does not interact with the light by which you see. This analogy captures something essential about the relationship between dark matter and ordinary matter. They coexist. They occupy the same universe, the same galaxies, the same regions of space, but they interact with reality in fundamentally different ways. Ordinary matter participates in all four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. It can form atoms, molecules, complex structures, chemistry, biology. It emits and absorbs light. It's visible, tangible, interactive. Dark matter participates in gravity and possibly nothing else detectable. It cannot form atoms. It cannot form complex structures. It cannot emit or absorb light. It's invisible, intangible, and structurally simple. But it is gravitationally dominant. There is more of it, and it shaped everything. The two kinds of matter are like two populations inhabiting the same city, but living on different planes of existence. Ordinary matter builds the shops and houses and parks and roads. Dark matter determines where the hills and valleys are, where the rivers flow, where the ground is firm enough to build on. Ordinary matter is colorful, complex, and dynamic. Dark matter is unseen but foundational. Remove the ordinary matter and you have an invisible landscape with no one to walk on it. Remove the dark matter and the landscape itself disappears. And there is nowhere for ordinary matter to build. This is the deep answer to the question of why we've never seen dark matter. It is not a failure of our instruments. It is not a limitation of our technology. It is not that dark matter is hiding or evading detection. It is that dark matter, by its very nature, does not participate in the interaction that all of our seeing depends on. Every image we have ever taken, every observation we have ever made, every measurement of any object in the universe has been mediated by the electromagnetic force. And dark matter is the one thing in the cosmos that is completely deaf to that force. It doesn't hear the electromagnetic call. Photons pass through it without noticing it's there. It passes through photons without noticing they're there. The two do not communicate. They share the same universe, obey the same gravity, but in the electromagnetic realm, they might as well be in separate realities. This is why every telescope ever built, at every wavelength, has failed to see dark matter. Not because the telescopes aren't powerful enough, but because they're asking the wrong question. They're listening on a frequency that dark matter doesn't broadcast on. They're looking for electromagnetic signals from something that doesn't emit, absorb, or interact with electromagnetic radiation. You could build a telescope 1,000,000 times more sensitive than the James Webb Space Telescope, observing at every wavelength simultaneously, and you would still see exactly zero dark matter. The problem is not sensitivity. The problem is physics. Dark matter doesn't talk to light. Period. And that is what structurally distinguishes dark matter from every known particle. The photon, the gluon, the neutrino, the electron, the quark, the proton, the neutron, every one of them participates in at least one non-gravitational interaction that we can exploit to detect it. The photon is the electromagnetic interaction. The gluon mediates the strong force. The electron interacts electromagnetically. Quarks interact through both the electromagnetic and strong forces. The proton and neutron are composites of quarks and gluons, participating in electromagnetic and strong interactions. Even the neutrino, the most elusive of all known particles, interacts through the weak force at a rate that allows detection. Dark matter has none of these handles, no electromagnetic coupling, no strong force interaction, no confirmed weak force interaction. Gravity alone connects it to the rest of the universe, and gravity at the particle level is too weak to be a practical detection tool. We can see dark matter's gravity when it operates on the scale of galaxies and galaxy clusters and the cosmic web, but we cannot see it at the scale of individual particles. We are left in the extraordinary position of knowing that the majority of the matter in the universe exists. Knowing where it is, knowing how much there is, knowing what it does to the things around it, and yet being completely unable to see it, touch it, or interact with it in any direct way. This is not a temporary situation that will be resolved with better technology. It is a consequence of what dark matter fundamentally is. Unless dark matter has some interaction beyond gravity that we haven't yet been able to measure, some extremely weak coupling to ordinary matter through the weak force or through some as yet unknown force, then dark matter will remain forever invisible to electromagnetic observation. We will never photograph it. We will never image it. We will never see it glow or cast a shadow or reflect a single photon. We will only ever see what it does to the things we can see. Its influence, its gravity, its fingerprints on the visible universe. And yet, those fingerprints are everywhere. In the rotation of every galaxy, in the bending of light around every cluster, in the pattern of the oldest radiation in existence, in the architecture of the cosmic web, in the very existence of stars, planets, and life. Dark matter shaped everything we see. It built the universe we inhabit. It was the first structure to form after the Big Bang, the gravitational scaffolding into which all visible matter fell. And then it disappeared from view, not because it left, but because it was never visible in the first place. It did its work through gravity alone, the quietest and most democratic of forces, the force that acts on everything regardless of composition, the force that doesn't need electromagnetic coupling to make its presence known. Dark matter is not missing. It is not hidden. It is not absent. It is everywhere, right now, passing through the Earth at hundreds of kilometers per second, streaming through your body without disturbing a single atom, filling the halo of the Milky Way with roughly 10 times more mass than all the stars you can see combined. It is the majority. We are the minority. And the only reason we know it's there is that gravity, feeble as it is, cannot be silenced. Gravity speaks even when light is mute, and dark matter, invisible to everything except gravity, has been speaking to us through the motions of galaxies and the bending of space-time for nearly a century. We just had to learn how to listen. So we know dark matter is there. The gravitational evidence is overwhelming. 6 independent lines of observation, using different physics, different instruments, different epochs of cosmic history, all converge on the same conclusion. Something invisible, something massive, something that does not interact with electromagnetic radiation, constitutes roughly 85% of all the matter in the universe. We know where it is. We know how much there is. We know what it does to the visible universe around it. But we still don't know what it actually is. We don't know what particle, if it is a particle, makes up dark matter. And despite decades of searching with the most sensitive instruments ever conceived, no one has directly captured a single piece of it in any laboratory on Earth. This might seem like a contradiction. How can we be so certain that something exists if we've never held it in our hands? But certainty in science doesn't require direct contact. We were certain that atoms existed decades before anyone could image one. We were certain that the Earth orbited the Sun centuries before anyone left the planet and looked back. Evidence doesn't require touching. It requires consistency, reproducibility, and the convergence of independent measurements. Dark matter passes all of these tests. What it hasn't passed, not yet, is the test of direct particle detection. Let me walk you through the 3 main strategies scientists are using to try to catch dark matter at the particle level. Because even though these efforts have so far come up empty, understanding them reveals how close we are to the boundary of the known and how much remains on the other side. The first strategy is called direct detection. The logic is beautifully simple. If the Milky Way is surrounded by a dark matter halo with the mass and density that gravitational observations demand, then dark matter particles are everywhere around us. They're not confined to distant galaxy clusters or the outskirts of spiral arms. They fill the space we occupy right now. Estimates based on the local dark matter density suggest that hundreds of thousands, perhaps millions, of dark matter particles pass through every square centimeter of the Earth's surface every single second. They stream through buildings, through mountains, through the entire planet, and almost every one of them passes straight through without interacting with a single atom. Just as most neutrinos do, but apparently even more so. The word almost is where the hope lies. If dark matter has any interaction with ordinary matter beyond gravity, even an incredibly faint one, then very occasionally, purely by chance, a dark matter particle might collide with an atomic nucleus. The collision would transfer a tiny amount of energy to the nucleus, causing it to recoil. That recoil, if the detector is sensitive enough, could be measured. Direct detection experiments are engineering marvels designed to catch exactly this kind of event. They use large volumes of carefully chosen materials. Liquid xenon is one of the most popular choices because xenon nuclei are heavy, making them better targets for collisions, and because liquid xenon produces detectable flashes of light and tiny electrical signals when a nucleus is struck. Other experiments use germanium crystals, silicon, sodium iodide, or calcium tungstate. The detector materials are purified to extraordinary levels, removing every possible trace of radioactive contamination that might produce false signals. The detectors are cooled to temperatures near absolute zero. and they're placed deep underground, in mines and tunnels, buried beneath kilometers of rock that shields them from the constant rain of cosmic ray particles that bombard the Earth's surface from space. The sensitivity of these instruments is staggering. They can detect energy deposits of just a few kilo electron volts. To put that in perspective, that's roughly the energy carried by a single photon of ultraviolet light. These detectors can feel the gentlest possible nudge of an atomic nucleus, the faintest conceivable signal from a collision with an unknown particle. And yet, after decades of operation, involving collaborations of hundreds of scientists, costing hundreds of millions of dollars, none of these experiments has produced a confirmed detection of the dark matter particle. The Xenon collaboration, operating in the Gran Sasso laboratory, deep beneath the Apennine Mountains in Italy, has published some of the most sensitive results ever achieved. Nothing. The LX Zeppelin experiment, operating nearly a mile underground in the Sanford Underground Research Facility in South Dakota, has reached sensitivities that would have been considered impossible a generation ago. Nothing. The Pandex experiment in China, nothing. Each experiment, with each new run, pushes the upper limit on dark matter's interaction strength lower and lower, telling us that if dark matter does interact with ordinary matter through some non-gravitational force, it does so even more rarely than we previously thought. The second strategy is indirect detection. Instead of waiting for a dark matter particle to bump into an ordinary atom, this approach looks for the byproducts of dark matter particles interacting with each other. Many theoretical models predict that when two dark matter particles meet, they can annihilate each other, converting their mass into energy in the form of ordinary particles. Photons, electrons, positrons, neutrinos. These annihilation products would be detectable with existing instruments if they're produced in large enough quantities. The best places to look for these signals are regions where dark matter is expected to be densely concentrated. The center of the Milky Way, where the dark matter halo is densest. The centers of nearby dwarf galaxies, which are among the most dark matter-dominated objects in the universe. Even the Sun, which might gradually accumulate dark matter particles in its core through gravitational capture over billions of years. The Fermi Gamma Ray Space Telescope has been searching for gamma ray signals from dark matter annihilation since 2008. It surveys the entire sky in gamma rays, the highest energy form of electromagnetic radiation, looking for excess emission that can't be explained by known astrophysical sources. In 2009, researchers identified a curious excess of gamma rays coming from the center of the Milky Way. The signal had roughly the right energy spectrum and spatial distribution to be consistent with dark matter annihilation. For a few years, excitement built. Was this the first indirect detection of dark matter? But further analysis complicated the picture. Other researchers showed that the same signal could be explained by a large population of millisecond pulsars, rapidly spinning neutron stars that emit gamma rays but are individually too faint to resolve. The galactic center is a crowded, complex environment with many sources of high-energy radiation. Distinguishing a dark matter signal from the astrophysical background is extraordinarily difficult. The excess remains unexplained, but it has not been confirmed as dark matter. The signal is ambiguous. It might be dark matter, it might be pulsars, it might be something else entirely. Other indirect searches have looked for excess positrons in cosmic rays, for unexplained X-ray lines from galaxy clusters, for neutrinos from the sun's core that might signal captured dark matter annihilating inside it. Some of these searches have produced intriguing hints. In 2014, an unidentified X-ray emission line at an energy of about 3.5 kilo electron volts was detected from several galaxy clusters. This line was consistent with the decay of a hypothetical particle called a sterile neutrino, which is one of the dark matter candidates. But subsequent observations have produced conflicting results. Some telescopes see the line, others don't. The signal remains controversial and unconfirmed. The pattern across all indirect detection efforts is the same. Occasional tantalizing hints, followed by ambiguity, followed by the realization that known astrophysical processes can explain the observations without invoking dark matter. No confirmed indirect detection has been made. The third strategy is production at particle colliders. The Large Hadron Collider at CERN, straddling the border between Switzerland and France, is the most powerful particle accelerator ever built. It accelerates protons to within a fraction of a percent of the speed of light and smashes them together at energies of 13 tera-electron volts. These collisions produce showers of particles, some familiar, some exotic, all governed by the fundamental forces of nature. If the dark matter particles have masses within the energy range accessible to the Large Hadron Collider, and if they interact with ordinary matter through any force strong enough, then these collisions might produce dark matter particles. You wouldn't see the dark matter particles directly. They would pass through the detector without leaving a trace, just as they pass through everything else. But you'd notice something missing. The total energy and momentum of the visible particles produced in the collision would add up to less than the energy and momentum of the incoming protons. The deficit, the missing energy, would be carried away by the invisible dark matter particles. This missing energy signature is what physicists search for. The Large Hadron Collider has been searching for these signatures since it began full operation. Thousands of physicists analyze billions of collision events, looking for patterns of missing energy that match what dark matter production would look like. So far, nothing has been found. No excess of missing energy events above what's expected from known processes like neutrino production. The collider has set limits on the masses and interaction strengths of potential dark matter particles, ruling out certain theoretical possibilities, but it has not discovered dark matter. Despite the absence of a detection through any of these three methods, physicists have developed several theoretical candidates for what dark matter might be. These candidates are motivated by well-established principles of particle physics, and each makes specific predictions that can, at least in principle, be tested. The most extensively studied candidate has been the WIMP, which stands for Weakly Interacting Massive Particle. WIMPs are hypothetical particles with masses somewhere between roughly 1 and 1,000 times the mass of a proton. They would interact through the weak nuclear force, or through a force of similar strength, in addition to gravity. The appeal of WIMPs came from a remarkable numerical coincidence, known as the WIMP miracle. If you calculate how much dark matter would have been produced in the hot, dense conditions of the early universe, and you assume the dark matter particles have weak force scale interactions with ordinary matter The amount of dark matter left over after the universe cooled matches the observed amount almost exactly. This coincidence was striking. It suggested that dark matter might be naturally explained by a particle with properties in a range that experiments could probe. This motivated decades of experimental effort. Direct detection experiments were designed specifically with WIMPs in mind. Their target sensitivity, the masses and interaction strengths they were built to probe, were calibrated to the WIMP hypothesis, and for a long time, the WIMP was considered the leading dark matter candidate. But the searchers have not found WIMPs. The most sensitive experiments have now excluded the parameter space where the simplest WIMP models predicted particles should be. The original WIMP miracle is not dead, exactly. There are more complex WIMP models that predict particles with lower interaction rates, models that haven't been fully tested yet. But the simplest and most natural versions of the WIMP hypothesis are under severe pressure. The miracle is looking less miraculous than it once did. Another candidate that has gained increasing attention is the axion. Axions were not originally proposed as dark matter candidates at all. They were invented to solve a completely different problem in particle physics called the strong CP problem. This problem asks why the strong nuclear force, which governs the behavior of quarks and gluons inside protons and neutrons, respects a particular symmetry called CP symmetry. There's no obvious reason why it should. The equations of the strong force allow CP violation, but experiments show that the strong force conserves CP to extraordinary precision. In 1977, Roberto Peccei and Helen Quinn proposed a mechanism that would naturally explain this observation, and their mechanism predicted the existence of a new, very light particle. Frank Wilczek and Steven Weinberg independently worked out the properties of this particle and named it the axion. If axions exist, they would be extraordinarily light, perhaps a millionth of an electron volt in mass, or even less. That's roughly 1 trillion times lighter than an electron. They would interact with ordinary matter so weakly that they make neutrinos look gregarious by comparison. But here's the key insight. If axions were produced in the early universe in the right way, through a process called vacuum misalignment, they could have been produced in enormous numbers. Their individual masses are tiny, but there are so many of them that their collective mass could account for all the dark matter in the universe. Axion detection requires a completely different approach from WIMP detection. The axion dark matter experiment, known as ADMX, uses a powerful magnetic field and a precisely tuned microwave cavity. If an axion passes through a strong magnetic field, there is a tiny probability that it will convert into a photon. The microwave cavity is designed to amplify these converted photons, making them detectable. The experiment has been running for years, gradually scanning through different axion masses by tuning the cavity's resonant frequency. So far, no detection has been made, but significant portions of the theoretical parameter space have been explored, and the technology is steadily improving. Other axion experiments using different techniques are also underway around the world. Sterile neutrinos represent yet another possibility. The 3 known types of neutrinos, electron neutrinos, muon neutrinos, and tau neutrinos, all interact through the weak force. A sterile neutrino would be a hypothetical 4th type that does not interact through any standard model force at all. It would interact only through gravity and through extremely suppressed quantum mixing with ordinary neutrinos. If sterile neutrinos have masses in the range of a few kilo-electron-volts, they could be produced in the early universe in quantities sufficient to account for dark matter. And if they decay very slowly, over timescales far longer than the age of the universe, they might occasionally produce an X-ray photon that telescopes could detect. This is the origin of the 3.5 kilo-electron-volt line I mentioned earlier. Some observations are consistent with sterile neutrino decay, others are not. The question remains open. There are also more exotic possibilities. Primordial black holes, formed not from collapsing stars but from extreme density fluctuations in the first fraction of a second after the Big Bang, could in principle account for some or all of the dark matter. These wouldn't be particles at all. They'd be gravitational objects, tiny black holes with masses that could range from less than the mass of the Moon to many times the mass of the Sun. Observations have constrained the allowed mass ranges significantly. Gravitational microlensing surveys, which look for the brief brightening of background stars when a compact massive object passes in front of them, have ruled out primordial black holes in many mass ranges. But some windows remain open. The idea hasn't been killed. The critical point in all of this is that every single one of these candidates remains theoretical. WIMPs have not been found, axions have not been found, sterile neutrinos have not been confirmed, primordial black holes have not been identified as the dominant dark matter component. No particle or object has been directly detected and confirmed as dark matter. This is not a weakness of the dark matter hypothesis itself. The gravitational evidence for dark matter's existence is rock solid, independent of what dark matter turns out to be made of. But the identity of dark matter, the answer to the question of what it actually is at the microscopic level, remains one of the most important unsolved problems in all of physics. Before we close, let me address one final source of confusion that trips up almost everyone who encounters this subject for the first time. Dark matter is not dark energy. These are completely different phenomena that happen to share the word dark for the simple reason that we don't fully understand either of them. The similarity in names is unfortunate because it leads people to conflate two entirely distinct mysteries. Dark matter is a form of matter. It has mass, it clumps, it forms halos around galaxies and scaffolding for the cosmic web. It participates in gravitational attraction, pulling things together. It makes up about 27% of the universe's total energy content. Dark energy is something else entirely. It is a property of space itself, an energy associated with the vacuum that causes the expansion of the universe to accelerate. Dark energy does not clump. It does not form structures. It does not pull things together. It pushes them apart. It is spread uniformly throughout all of space, and its effect grows as the universe expands because there is more space for it to fill. Dark energy makes up about 68% of the universe's total energy content. Ordinary matter, the atoms and molecules and particles that make up everything we can see and touch and measure directly, accounts for roughly 5%. 5%. Every star, every planet, every galaxy, every gas cloud, every dust grain, every atom in every living organism on Earth, all of it combined is 5% of the universe. The remaining 95% is split between two things we don't understand in any known way. The only thing they in any known way. The only thing they share is the word dark, which in physics simply means we don't know what it is. Dark matter is also not antimatter. Antimatter is ordinary matter with reversed quantum properties. A positron has the same mass as an electron, but a positive charge. When matter and antimatter meet, they annihilate completely, converting all their mass into gamma-ray photons. If dark matter were antimatter, we would see gamma-ray emission wherever dark matter encountered ordinary matter, at the boundaries of dark matter halos, in the dense centers of galaxies. We see nothing of the kind. Dark matter is not antimatter. Dark matter is also not ordinary matter that merely happens to be dark. Not black holes, not rogue planets, not cold gas clouds, not burned out stars. These objects are collectively called MACOs, massive astrophysical compact halo objects. Extensive searches for MACOs using gravitational microlensing have found some, but nowhere near enough to account for the total dark matter budget. The vast majority of dark matter cannot be any form of ordinary baryonic matter. So where does this leave us? What do we actually know? And what remains unknown? We know dark matter exists. We know it has mass. We know it interacts gravitationally. We know it does not couple to electromagnetic radiation. We know it does not participate in the strong nuclear force. We know that if it has any weak force interaction, it is below the threshold of our most sensitive experiments. We know it forms enormous halos around galaxies. We know it connects galaxies through filaments in the cosmic web. We know it was the first structure to form after the Big Bang, collapsing before ordinary matter and building the gravitational wells that seeded all visible structure. We know there is roughly 5 times more of it than all the ordinary matter in the universe. And we know it is not made of any known particle. Whatever dark matter is, it is something new. What we don't know is what dark matter particles are. We don't know their mass. We don't know if dark matter is a single particle species or an entire sector of particles with its own internal forces and interactions invisible to us. We don't know whether it was produced thermally in the Big Bang or through some exotic mechanism. We don't know whether the question has a simple answer or a complicated one, and that is where we stand. At the edge of an enormous unknown, staring across a boundary between what we can measure and what we cannot yet reach. Knowing that the majority of the matter in the universe is something we have never directly touched. Something that built everything we see and then vanished from electromagnetic view, leaving only gravity to tell us it was ever there. There is something profound about this. We live in a universe where most of the matter is invisible, not metaphorically, literally, physically. The universe is mostly made of something that does not interact with light. Everything we have ever seen, every image, every photograph, every observation in the history of astronomy, all of it captures only the minority component, the bright fraction, the 5%. The rest is dark, silent, present but unreachable by any telescope at any wavelength. And yet dark matter built everything. The galaxies we photograph formed inside dark matter halos. The cosmic web we map was sculpted by dark matter's gravity. The very planet you're standing on exists because dark matter collapsed first in the early universe, creating the gravitational wells that drew in the ordinary matter that eventually became stars and planets and oceans and air and you. Without dark matter, The density fluctuations in the cosmic microwave background were too small, and the time too short for ordinary matter to build galaxies on its own. Without dark matter's scaffolding, there would be no Milky Way, no sun, no Earth, no one to wonder about any of this. The invisible majority built the visible minority, and then it stepped aside, remaining forever transparent to the light that the visible minority uses to see. When you look up at the night sky, you see stars. You see the luminous band of the Milky Way. You see, if you know where to look, the faint smudge of the Andromeda galaxy 2.5 million light years away. All of it is ordinary matter, the 5%, the glowing, radiating, electromagnetically active fraction of the universe. But surrounding every galaxy you see is a vast halo of dark matter that you will never see. Connecting those galaxies are filaments of dark matter that no telescope will ever image. Filling the space around you, streaming through the Earth, passing through your body at this very moment, are hundreds of thousands of dark matter particles per second. They are the majority. You are the minority. And you will never feel them. Not one. For nearly a century, dark matter has been the deepest material mystery in physics. Fritz Zwicky noticed the first hint in 1933 and was ignored. Vera Rubin confirmed it in the 1970s and changed everything. Since then, the evidence has arrived from every direction. Gravitational lensing, the cosmic microwave background, large-scale structure, the bullet cluster, computer simulations, each piece independent, each pointing the same way. The universe is not what it appears to be. Most of it is hidden. And what's hidden shaped everything that's visible. We don't know what dark matter is made of. We may not know for decades. We may not know in our lifetimes. The particle, if it is a particle, might interact so weakly with ordinary matter that no experiment we can currently imagine will catch it. Or the next generation of detectors might find it tomorrow. That's the nature of searching at the frontier. You don't know what you'll find until you find it. And sometimes the most important discoveries are the ones that take the longest to arrive. But whatever dark matter turns out to be, one thing is already clear. It is the most abundant form of matter in the universe. It interacts through gravity, but not through light. It built the scaffolding of the cosmos, and it remains, after nearly a century of searching, the greatest invisible presence in the physical world. The next time you look up at the stars, remember what you've learned. You're seeing the 5%, the luminous fraction, the visible minority. The rest, the 27% that is dark matter, is there too, surrounding every galaxy, threading through every filament of the cosmic web, closer than the air you breathe, yet forever out of reach. You just can't see it. No one can. Not because we haven't looked hard enough, but because dark matter doesn't speak the language of light. And yet we found it anyway. Through gravity. Through the patient, careful observation of how visible things move. Through the bending of space-time and the wobbling of stars and the patterns in the oldest light in the universe. We are the 5%, and we discovered the 27% using nothing but mathematics, ingenuity, and the stubborn refusal to ignore what the numbers were telling us. That might be the most extraordinary thing about this entire story. Not that the universe is mostly invisible, not that most matter doesn't interact with light, but that creatures made entirely of the 5% living on a small planet orbiting an ordinary star in one galaxy among trillions, figured it out. We noticed the universe was heavier than it looked. We measured the discrepancy. We tested it from every angle. And we concluded with overwhelming confidence that something vast and invisible fills the cosmos. We can't see it. We can't touch it. We don't know what it's made of. But we know it's real. We know it's everywhere. And we know it built the universe we call home. Dark matter is out there. Invisible, massive, and everywhere. Holding galaxies together with nothing but gravity, shaping the largest structures in the cosmos, woven into the fabric of everything we see, yet touching none of it. The majority of the universe, silent and unseen, and yet, here you are, made of ordinary matter, made of the 5%, standing on a small world, looking up at the stars, aware that most of what surrounds you is something you'll never see, knowing that the darkness between the stars is not empty. It's full of something ancient and massive and foundational, something that was there before any star ignited, something that will be there long after the last star burns out. That's what dark matter really is, the invisible architect of everything visible, the silent majority, the gravitational backbone of the cosmos, and the deepest material mystery that science has ever faced. Thank you for joining me on this journey. If you found value in this exploration, a like or subscribe would mean the world. It helps me keep making these deep dives into the cosmos. And remember, the next time you look up at the night sky, you're not just seeing stars, you're seeing the 5%. The rest is there too. You just can't see it. But now you know it's there. And knowing that changes everything. Good night. And may you never look at the darkness between the stars the same way again.